All right, so this is an example for class 17 where I go through the power screw in completeness. Let's see. And I'm hoping that I have all of this in here. Okay, yep. So anyway, we want to answer the following. A single-threaded 25 millimeter power screw is 25 millimeters in diameter. No duh, 25 millimeters. With a pitch of 5 millimeters. A vertical load on the screw reaches a maximum of 5 kilonewtons. The coefficients of friction are 0.06 for a collar and 0.09 for the threads. The friction diameter of the collar is 45 millimeters. So we want to find the overall efficiency. We want to find the torque to raise and the torque to lower the load. Find out if it's self-locking and estimate the torque required that would permanently damage the threads if the yield strength is 280 megapascals. So we start here, and I'm going to cop out by just revealing something I've already written. This is actually a scan of my hand. So I'm writing out that the outside diameter is 25 millimeters, and the pitch, that's supposed to be a P right there, it'll be revealed in a second as to be a P, is 5 millimeters, and the force applied is 5 kilonewtons. So the root diameter is going to be the outside diameter minus 1 pitch, because remember the pitch depth is P over 2, so we have 2 pitch depths, so we have minus P. And then the mean diameter is going to be just the outside diameter minus 1/2 right there. And the collar diameter was given to us, the friction diameter it is. And so taking a look over there, as you could see, we have 5 over 2, 5 over 2, so that just reinforces that. So we want the torque to raise that. I've decided to go use that one first because if we want the overall efficiency, we need the torque to raise, so we might as well get that. That's also going to be not just the thread friction, but also is going to be the collar friction, torque due to the collar friction. So we throw the numbers in there, right? Make sure that, where we have L, you notice that's going to be the same thing as the pitch, right? The lead is equal to the pitch if it's a single threaded piece. And it's a good idea to kind of figure out how much of this final answer is going to be the torque due to the collar. And it's quite a bit. This is also going to be useful to that we grabbed the torque due to the collar when we go and find the torque to lower. You notice the big differences here in these are going to be what's on the numerator and the denominator. And what we end up finding here is we have 7.83 Newton meters. So it takes less to lower it than it does to raise it, which kind of makes sense. So if we want to get the efficiency of the threads here, we take this equation, which is really just the raising one, but setting the coefficient of friction to 0, and we end up getting 3.979. So that's just the torque that's required just simply to lift the thing, right? Not forget about there even being any friction. Therefore, the efficiency is going to be 25.1%. Now, if we want to get the stress that's in the, and I don't think I answered this question right here. I don't think I copied this down into this right here. So I need to come back and answer the question, is it self-locking? Maybe I did later, but let's do it anyway. The self-locking occurs when the tangent of theta, well, it really should just be theta, not theta, lambda. Tangent of lambda is equal to L over pi dm, right? So that means that that's going to be 5, because that's the pitch, right? Divided by pi, divided by 22.5. And we end up getting 0.0704. right? And if these are small enough, by the way, the tangent and lambda equal each other, right? So we could even have done that in radians. But because this 0.07074 is less than 0.09, it's self-locking. All right, so I think I forgot to scan that part and clip it back in here. Now, to find the thread stress, we need to find out what the torque required to permanently damage. We use that yield strength, and we find the force that will exceed that 280 megapascals. So when the von Mises stress is greater than that, we have damage. So let's try to figure out the torque. In order to do this, to find these stresses, and assuming we had an arrangement where the torsion was on the correct side, we would need to know the torque, right, to find that. So it ends up being just a little bit more complicated if we end up including it. So let's ignore it as part of the estimate. So I get the bending stress. I believe I'm right. This is for some reason. Yes, in here I was saying, okay, so what I had originally said, so I ignored the stress for my first part, and then if I can ignore the shear, then all I need to do is for the von Mises is to use the one that uses only principal stresses, which, if you'll recall, it's important to go back and look this up in chapter 5, looks like this right here. And so we're going to have stress on one side that's going to be due to bending, and we're going to have stress on another side that's, so like if we had this right here, we're going to have a stress that's right here due to bending, and we're going to have a stress right here that's due to compression, right? So this is, and for us is going to be sigma A and sigma B. And so we take sigma A, in this case, is going to be the bending stress. So that's, and on the first thread, that's 38% is held by that first thread. So that's the one that we use. And we apply this. We end up finding, we get 7,257 times F, because we don't know F yet. And then due to the compression that's being placed on there, we have once again, only 38%. So it's going to be less and less as we move up. I kind of think perhaps in hindsight, I should have not made this 38% and made it the entire thing because of the stress, on that first thread. If we're drawing this onto this right here, and we're looking at this, we really should be looking at that first cube right there. Oh, I need to erase that thing. This first cube that's right there, right? Just right onto there. And if that's the case, it's going to have pretty much the entirety of the compression. So I'm kind of already thinking that maybe I should have had that. What I get is a negative 1210. So I go ahead and apply this right here, and I get 7,931. If we set these things equal to each other, right, we say that it's 35.3 kilonewtons. And if we use that 35.3 kilonewtons, we end up getting 112 newton meters. And we should probably have figured out what the shear stress with our equation for shear stress in the thing. And that would have been, where'd you go? That would have been 16t divided by pi dr. All right, so that's 112 newton meters divided by my pi and my dr. No, that's supposed to be dr cubed? Yeah, dr cubed. And what did I say my dr was equal to? Was going to be 20 millimeters, so 0.02. And I can calculate that right now. We can see if it's significant. And I take 112 times 16 and divide by pi, and then divide by 0.02 raised to the third, and divide, whoops, I got to do it again. 112, 16 times pi divided 0.023 raised to the thing, divide, and I get, it's going to end up being 71.3 megapascals. So not insignificant compared to what our strength was. What did I say? Our strength was going to be like 280. So maybe I want to go back and stick that back in. I think I also could have solved this by plugging in what my torque was going to be. It's simply going to be T times F times dr over 2. I think that's what we would say. Although no, actually it would be all due to this thing. I'm sorry, yeah, it would be due this entire thing. So that's the reason why I didn't plug it in. So I might actually make this in Excel and then do a goal seek to find out what that force was. That would be probably a preferred way to approach the thing. But you could see that it's just a little bit more effort. I guess if I went ahead and I calculated all of this right here and set that as a coefficient in front of F, I could have placed it into my von Mises stress larger equation that included my torque. But I think it was too long of algebra to take care of. So another problem that we might work out, but I'm not doing it here, is to find the stress in a C-clamp. And we want to try to determine which is going to fail first, the threads or the curved beam. Well, that's going to be sort of an up in the air depending on the means at which that you try to compare them, right? So one way that you could compare is to figure out the amount of force that's required inside here to be able to break the thing. Another is to maybe take and find out what the safety factor is. If you assume a load that's inside there and you have the safety factor based on the material, because this is a different material, it's cast iron, and this we could assume it's like stainless steel. We could assume those things, and we could get a safety factor, we could compare them. So that would determine which was going to fail first. It might be more interesting to find out what the load was going to be. We might be able to scale the load, maybe. I believe we would be able to scale the load because it is a linear thing, the stress and the load. So we could probably go backwards and do that way. So anyway, there's where the stresses will appear in your curved beam. That's interesting enough. And then here's also, I did some threads as part of this, and I did not make them, I didn't give them any lead or any angle to them. But you can see how those stresses are largest there in the front, and they get smaller and smaller as they go back. So it's an interesting thing that this has to be done with something called gap elements. They're kind of hidden away in SolidWorks. They just have surfaces, and what they essentially are is sort of a switch that gets turned on if they're in compression. Then yes, but if they have no contact or they end up in tension, they switch off, and the nodes don't cause any stress. So that is our solution there to our example problem. And it only took 14 minutes. But let's see. We have a really odd really odd looking guitar, or an odd guitar. It's not odd looking guitar. I got to put some batteries inside the little thing here. So you're probably not seen one of these. This is a Chaos pedal. Or a Chaos pad. It's a mini version of something that maybe DJs use. And some of my batteries are dead, so this might not work the first time, which is a really exciting video, I know. So let's see if it turns on. I'm going to hold the button down. It's going to load up. It's loading and it's working. All right, we're going to see a battery symbol on there. Yeah, it's got a little bit of a battery left right here, but it's got a little pad right here. It's got a bunch of different filters. And this guitar is actually fitted, it came this way, fitted with a little chunk taken out of it and some cables that are attached. And I always attach the cable the wrong way. So I should probably mark that down somewhere, which one's the input and which one's the output. But in many things in life, we just go ahead and let chaos rule. Oh, the interesting choice of words is this is a Chaos. I'm going to say it's a pedal. It's not really a pedal per se. And then let's see, we plug this sucker in. And in the guitar itself has a little distortion pedal built into it, a little fuzz box. And we need a battery for that. And I could have prepped all this ahead of time, right? So maybe I'll show this during class too. So this will be like something to look forward to. I'll probably run out of guitars if probably not. I don't know. Some of them aren't all that interesting. Some of them are just pieces of crap that are sitting around. Some of them are very similar to each other, so there's not like, don't tell my wife I said that. So let me see if this thing makes noise. It's not making no noise, which is really good grammar here. So I got everything plugged in here. What's going on? I think, let's see, is it this guy? Is it backwards? It's always backwards. Why are you making no noise? Okay, so that's some of the problem right there, is that this, do I have the wrong plug-in? Do I have the wrong cable? No, that's the right cable. And you're plugged in. And why are you making no noise? Why you do that? He says he's on. And his output level's on. Oh, the tuner is on. Wouldn't you know it? Turn the tuner off, buddy. Okay, so to get the full effect, you really need to see we got the tuning song. We got to tune it a little bit. It doesn't really matter. It's not that exciting of a musical instrument. It's more of a noise instrument. So if you're familiar with the band Muse, he has something similar built into his guitar, a much more expensive thing. This is all of like a $200 guitar. So it has a distortion circuit built into it. It's just like a little fuzz. And it's mostly because this chaos needs to be driven there. So when we engage the chaos, And there's a lot of other things this thing does, including, I don't know, this is called a morphing figure. And probably one of my favorite ones, well, okay, no, here's a vowel one. It's not my favorite one, but it's pretty cool. It sounds a little bit like talking, maybe a little bit. The vinyl break is my favorite one. For making noise. This was like a $200 guitar. Ooh, gotta get Jet. That's pretty cool. So that was worth money well spent, right? Because you could definitely do all kinds of crazy things with it. But I don't think I'd ever play this out like at a gig. Probably not for a while even now, because I don't know. It's getting kind of old to be playing in bands and going to people's backyards and not really going to bars very often. Delay. I don't know if the delay is any good in this. Now this thing is not actually made for a guitar. It's actually made for some, I don't know, some kind of techno DJ thingy, electronica kind of noise kind of thing. But one of the better ones that I like, and there's a ton of them on here, they got Slice Looper. I can't remember. Is that good? That's pretty cool. It's got a bunch of different loopers in there. I don't know, brake looper. What does that do? Let's see, there's a couple of really good ones that, oh, the battery just died. So I guess it's done, because the, one of these batteries isn't good. I have like 5 batteries sitting here, and one of the 5 is bad, and I don't know which one it is. So there you have it. This is the little Chaos thing and this little cheap Ibanez guitar. Was it worth $200? I don't know. So, that's all for now. 25 minutes into there, but a lot of it was me showing off on my guitar. Yeah, yeah, sure.